So at Dell Technologies, we believe that all businesses will need to partake in this sort of data era in order to become an intelligent business, and being able to reimagine the customer experiences in the product that we're delivering to our consumers and to the world, to help us to solve some of the big challenges that we're kind of focusing on. So when we think about as an individual organization, we have a lot of control over the data that we're collecting and the insight that we can build from that. But usually we're only a small part in the chain that we take to get the consumption to our end consumer. So we're starting to see these value chains being built up and to be imagined in software, where you're connecting together your suppliers and the people that you use in order to create your business, as well as your the logistics and supply chain that's connecting you to the end consumer of your particular product or service. All of the information that you can glean up and down that value chain allows you to get far more efficient and effective at how you can produce that technology and be able to get it into the hands of your consumer, and to make sure that you're doing that for the least possible cost and the maximum possible value. So we're seeing people like Sky TV, for instance. So Sky have transformed the way that they're operating with their customers and to produce a real data-driven method of doing customer service. So by using that integration across their supply chain, they know where the installers and suppliers of the TV transmission are. They know they can reach right into the transmission network, and they can see where the telecommunications are being used to be able to deliver the product into the marketplace. So when customers connect to them with a challenge or a problem that needs solving, they've built a digital model that allows them to understand where all of those pieces add up and where the challenges might be transferring. So they can start to narrow down exactly where the customer's being impacted, and to use that to scale out their customer service, to be able to resolve customer issues very, very quickly. So that's led to them having a dramatic drop in their customer services costs. So by building these digital avatars and chatbots, they've been able to reduce their reliance on call centers. They've allowed them to be able to react quicker to their customers and to be able to solve their customers' problems first time, rather than having to go through a triage of eventually sort of shifting some of those problems to the engineers in the background who can actually solve those. So that's led to a vast improvement in their customer satisfaction and net promoter scores. And we'll see these types of models where customers are connecting up their entire value chain and gaining that visibility happening more and more. And of course, these data sets now that we're collecting, they're getting large enough now for us to be able to build what we're calling digital twins. So a digital twin is really a digital instantiation of a physical object or a system that can be as small as an individual product that we're building, or it could be as large as an entire value chain. So we're seeing this, for instance, we've done a lot of work with GE, and GE build jet planes and jet engines. The jet engines are integrated onto the plane structure itself, and traditionally those engines would have been maintained or managed in compliance with a maintenance schedule that they'd agreed to with the FAA or the CAA, depending on where those planes are flying. So the airline would have needed to pull that plane out of production to be able to take it to pieces, to be able to make sure that the individual parts were wearing according to their predictions, and to replace those pieces that needed replacing. What we've been able to do now by building sensors right the way throughout the engines is that we've been able to take the data that's streaming off those engines in real time and apply that to a digital twin model of the engine. So we can actually see how the wearing of an individual part is impacting the performance of the engine, and how that's showing up in the sensors that we're seeing of that engine kind of in flight. So we can actually predict when that part is going to reach the point where it needs to be replaced. We can have the part and the engineer ready to meet the plane when it lands at its destination, so that that part can be replaced and the plane can be put back into service quickly and easily, before having to take it out of out of the environment. And that's actually created an opportunity for GE to create a completely new business model. So rather than selling the engines to the aircraft manufacturer, to Boeing or Airbus, and then selling them a maintenance contract where they're maintaining that engine over the next sort of 10 years, they're now selling those engines based on the number of thrust hours that they're delivering in production. So if the engine is out of production for any particular reason, they're not getting paid for that engine. So their goal is to be able to make sure that the engine is working and is delivering those outcomes in real time, right the way across the fleet. So that's become a real sort of opportunity for them to change the business model in which they operate. So we've seen these digital twins being used in lots of different ways, from being used during the product development cycle to be able to understand how the existing product is working in the real world, and then to be able to take a little bit like the sailing example I gave you earlier, to be able to try many different combinations of design to see how that will perform in the real world before it's actually implemented. Interestingly, as I said, I'm an angel investor and a mentor on one of the companies in which I've invested in here in New Zealand. Is called Formus Labs, who have taken MRIs and CT scans of human knees and been able to recreate that as a digital twin. And what they've been able to do is to take your individual MRIs and X-rays and to be able to put that onto the digital twin, to alter the digital twin to fit you and your exact needs as an individual human. In fact, I had this done sort of at the end of 2019. I had an accident about 5 years ago and destroyed the inner part of my knee and had a couple of surgeries, but nothing actually helped me being able to sort of walk without pain. So what they did is they took the damage that had been done to my knee and mapped that against the digital twin in the computer, and then modeled the operation that they wanted to do to re-architect my knee so that they could move the weight bearing through my knee away from the impacted and damaged part of my joint over towards the healthy part of my joint. So they were able to do that in the computer and see what that output looked like, and then produce a 3D printed wedge and a cutting guide that they used during surgery to be able to open my knee up and re-architect that to the way that it's to optimum elements for me, and then 3D printed a titanium brace to screw over the top of that to be able to hold it in place. And now I'm able to have no pain at all in my knee. I'm able to get back into sport and to be able to move. And in fact, that operation, the personalization that they were able to do with that allowed me to get far better outcomes than would have been able to do if they'd just taken a traditional kind of approach to that surgery. So we're seeing these digital twins being used in industry, being used in healthcare. We're seeing them being used for creating new decision points, and we're using them to be able to optimize processes across the environment. So we have a kind of a range of models. So we started with this sort of very basic model where we're thinking about a digital version of that and that we can manipulate. That very quickly starts to get augmented with sensors that we're pulling off the data in real time. So if you think about a robot in a factory, for instance, we can monitor its movement, its temperature, the wear, the maintenance that it's undergoing, and we can then start to build a digital twin that mirrors some of that, and we can start to use that to predict when we might need to do maintenance, much to the GE example that we're using. We've now got to the point where we can develop these level 2, or what we call clones of the digital twins of the environment. And that allows us to be able to take on design changes and to look at new generations of this capability and start to see what we might be able to improve these environments over time. And we're moving towards now this method of being able to augment the digital twins to be able to predict the future. So what we're starting to see, and especially with things like energy and utility pipelines and oil and gas, for instance, if we know that our production rates are going to go up and we're going to need to move, we can start to to run that in the digital model hours before that will actually happen in the real sort of factory that we're using. So we can start to see where things might get backed up, where pressure conditions might overcompensate, and to be able to predict what we're going to need to change before we need to change it in the real world. So we're starting to move towards these models becoming useful for predicting the future and for being able to understand how to best set up our physical environment to be able to handle the conditions that we can predict as we're moving forward. So someone asked if the slides will be available, so I will send these slides out afterwards. I'll turn them into a PDF, so they're a little bit easier to be able to transfer for you. But yes, I'll send these out afterwards, so you should be able to see this. Now, someone's asked in the Q&A if I have a solution overview. I've intentionally kept away from having this presentation too technical. I didn't want to dive into the technical detail. I wanted to keep it a bit more at an overview level to be able to understand, how these changing and emerging technologies are impacting that. I do have a bunch of that information, so I'm happy to give you some of that if you so want to. Just by all means, kind of reach out to me, and I can help provide some of that information for you. So as I said, these digital twins are very quickly becoming to the point where we can start to manage our manufacturing pipelines more effectively. And the digital twin is actually becoming more valuable than the physical asset in which it's being based. So we're starting to see this huge push towards driving some of these kind of methods. So in fact, IDC reckon that in the next few years, so by 2023, 30% of manufacturers will have digital twins set up of their plant and manufacturing facilities. That'll lead to an 80% reduction in logistics bottlenecks around the logistics of their factory and manufacturing facilities. 70% of the oil majors will be employing digital twins. We're already doing this with companies like Petronas, for instance, to be able to take the seismic measuring information that they've got on as they're exploring for new oil fields that they run in the sea, and we take that models and we use that to create a model of what the seabed looks like, to try to use then our experiential learning about where we're likely to find oil in these environments, and to be able to map that across the digital twin to be able to show where the best places are to be able to prospect for additional oil. We're also using it in terms of the oil pipelines and the manufacturing facilities, where we're starting to be able to predict efficiencies and effectiveness and how those pipelines are being built and being managed kind of moving forward. And as that part of those establishment processes, we're starting to see digital twins being used to lay out new pipelines and new facilities to make sure that they take full advantage of the effectiveness. We're also starting to map existing facilities. So we're starting to see this being used, and I'll talk to you a little bit about one of the other companies that I'm engaged with and how they're mapping out sort of existing facilities to do that. So one of the other examples I wanted to talk to you about was McLaren. So back in the early 2000s, the Formula One banned using doing modeling outside of race weekends. So the manufacturers weren't able to compete against each other and outside of the actual races themselves in order to be able to see where they needed to make improvements. So we started working with McLaren around how to build sensors through the cars and how to create a digital twin or a model of those cars, that we could do some of that practice and training and some of that augmentation in the digital model itself, rather than having to do that in the physical car and trying to do that during kind of race weekends. That led to an enormous speed up of their ability to be able to create new generations of cars, I think 40% faster in terms of their ability to be able to design new generations, and to be able to take, as the Formula One rules changed, and to be able to take those changes and then be able to model them in the digital model, and to be able to see what the impact of that was in the cars, and transfer that through to track times and how that would affect their ability to compete in those marketplaces. So they're collecting an enormous amount of data every time the car goes around the racetrack. And we've built a specific environment for them into one of their traveling containers that allows them to take all of that sensor data off the car, be able to store that, analyze that, and be able to run that against their digital twin. And they actually have that a few seconds ahead of the car itself, so that they can see when the stresses are going to build up, when the tires are going to wear down, when these things are going to need to change, and they can retune and remap the engine and change the setup of the car in real time while it's driving, based on what their model says the car is going to need in real time. So that's quite a cool sort of example that we're working with in that sort of realm. So this is the company I mentioned to you that I'm one of them that I'm working with, called Geocam. So Geocam have actually created a combined solution. There's the camera, which you can see in the center there. The camera is actually 3 fisheye sensors that are built on an ultra-stable kind of platform. That means that they can know exactly the position of those cameras in space. Each of those cameras overlaps with the other, so they're always getting at least 2 of those cameras seeing any particular kind of point in space. And built into the camera itself is actually an accelerator, an NVIDIA card, which helps to process those images in real time to be able to stitch them together. And then they've built a machine learning algorithm in the cloud that takes all of that imagery and uses that to recreate a digital model. So you can see here one of the jobs that they did for Amazon with one of the Amazon warehouses. You can see down on the bottom left there the warehouse itself and how that's kind of set up in the real world. And they actually took the cameras around the warehouse and used that because it's such an accurate, there's so much accuracy between the image overlaps. They don't need to use things like LiDAR and other distance measuring capability. They can actually use the difference between the 2 images to be able to tell exactly the distance to the point in which the image is being captured, right down to actually the millimeter precision level. So that's allowed them on the right-hand side of the screen there. This is actually the digital model of that facility. So you can move around this in 3 dimensions. You can map and measure this in real time. And in fact, I've got an example for you here, another one where they've used aerial mapping and drones with those cameras on them to be able to take this and to be able to apply it to a GIS kind of format. So this is actually a small town here in New Zealand called Oamaru, which is sort of halfway between Christchurch and Dunedin. If you know the South Island of New Zealand, it's sort of down in the lower half of the South Island. So these maps here are built through these cameras being mapped onto drones. And the drones have been able to fly around and take that aerial imagery, and then to be able to create the 3D mesh where they can map tiny pixels out of each of these images, and to be able to then assign those pixels into a 3D point cloud to be able to allow this image to be recreated from a database rather than overlaid by imagery. And it means you can actually do things like measure this in real time. So you can actually, because these are right down to the millimeter level, you can actually measure the height from the window to the ground, for instance, because you can see how these maps are being moving around, and you can see how close the imagery is being able to map to see exactly the height and distance of all of these features that are in this kind of 3D model of the real kind of environment. So they've been able to map this so that you can walk around and see the town kind of in real time from all these different dimensions that wouldn't have necessarily been open to you when you were traveling around the environment itself. So you can actually map this out. This is very useful for people who are, for instance, managing assets in a city. They can be able to see exactly how many manhole covers, how many power poles. They can start to map infrastructure against this, so they can start to see where telephone transmitters are in the environment. They can see all the pipelines, etc., that are underlaid. So you can overlay these models with all of this other information that allows you to be able to use this kind of in real time. Even to the point, because of the precision of these models, they can start to detect, for instance, compliance on whether ramps are at the right angle for being able to wheelchair access and disability access, by just doing this purely in the digital model rather than having to send an assessor out onto the real environment to be able to see kind of what's going on. So just the last example that I have here, which is a little bit fun, is a company we're working with in the USA called TopGolf. So TopGolf have built, we've built a system with them to be able to use RFID chips that are built into the golf balls, and to be able to tell exactly the speed and direction and how those are hit. So they can use that to create a real-time model of exactly the speed and angle and velocity by which the ball was hit, so that they can provide that feedback directly to the player in a coaching kind of format to be able to help them adjust their swing and adjust their game to make sure that they're going to achieve the right sort of performance outcomes in real time. So this is all built into they've got these machine learning systems that understand exactly how a change in an angle and attack will make a difference in where the ball is going, and then they've used that to be able to create insight from one shot to be able to drive that kind of back. So that was what I prepared for you today. I hope it was of use. I'm more than happy to take any questions, or if you've got any comments or insight that you'd like to share, I'm more than happy to take any questions that you might have.